Hello students, so today we are going to discuss about competitive electron transfer. So we already discussed about what is electron transfer. When something or any of the reactant loses electron, its oxidation state increases and it is called oxidation reaction. And when any of the reactant gains electron, its oxidation state decreases and it is called reduction. So by this electron transfer we can get redox reaction. So we are going to discuss about competitive electron transfer reactions. That means based on the reactivity of the given reactants, they will either lose electron or they will gain electron. And we already know this type of example. In earlier standards, that means in standard 6, 7 or 8, you already see this type of reaction. In earlier standard, reaction was mentioned like this. We have a solution of copper compound. Basically, normally we can use copper sulfate or copper nitrate. In this case, copper will be in +2 oxidation state, or it is +2 ion. And if we dip a nail of iron or anything made up of iron, let's say iron rod, which contains metallic ion, that means it contains zero oxidation state or zero charge. So when these two compounds work together or come in contact with each other, we have copper +2 and iron. So basically copper is less reactive than iron. So less reactive metal, that means it will stay in atomic state or metallic state. And higher reactive metals, usually they will try to convert themselves into ions or compounds form. That means by losing electron it can form positive ion. So reactive metals have comparatively low attraction to electrons, and less reactive or stable metals or noble metals have stronger attraction towards the electrons. So iron being more reactive than copper, it gives electron to the copper, and after reaction you will get copper metal and ions, that means Fe+2 and copper with zero oxidation state. So earlier we have solution of copper compound, that's why we can represent it with aqueous, and solid of iron. Later you will get solid of copper and aqueous solution of Fe. So what will be the visual hints or visual observation in this beaker? So copper sulfate solutions are usually blue. Copper compounds are usually blue in color. So you will see a dark or intense blue colored copper solution and an iron nail in it. Now as the reaction proceeds, blue color intensity decreases because copper sulfate is reducing into copper metal, and slightly greenish solution will start developing because iron compounds, that means in this case it will be FeSO4. So FeSO4, it has light green color. So light green colored solution will be observed and reduced copper metal will deposit on the surface of iron rod. That means red dots on the surface of iron rod will be observed. In short, iron reduces copper solution into copper metal. So our overall reaction in this case is copper +2 plus Fe gives copper metal and Fe+2. So we can separate out this redox reaction in two different stages, that means oxidation half reaction and reduction half reaction. So if oxidation state increases or if compound loses electron, then it is reduction. So oxidation. So in case of given reaction, Fe solid releases electron and converts into Fe2+. So this is oxidation. So this is called oxidation half reaction. On the second hand, this released electron will be gained or obtained by copper, and it will give us copper metal. So this is reduction reaction, because if electrons are gained then it is reduction reaction, and if electrons are lost then it is oxidation reaction. And combination of these two half reactions will be the overall reaction mentioned above. So same example is mentioned here. First example of copper and zinc is mentioned. As we can see here, we have visual representation of the reaction. So first we have a beaker which contains blue colored solution, which is copper solution, usually copper sulfate or copper nitrate. Then we dip a rod of zinc into it. So as we can see, blue color intensity in next image is decreasing and zinc metal develops red color at the bottom. So this red color represents copper metal formation. When copper ions are reduced into copper metal, it will deposit on the surface of zinc, and that's why we can see red color developing on the surface of zinc. At the same time, we can compare the intensity of the color of the solution. As we can see, color intensity decreases. As the reaction further proceeds, more and more reddish color will develop on the surface of zinc and less color of the solution will be observed. If you use iron metal, then you will see you will get greenish colored solution, but in this case we have zinc metal and zinc nitrate solutions are usually colorless, so you will see colorless solution at the end of the reaction. And this reaction is simply possible because copper metals are less reactive than this zinc metal. If we place copper and zinc according to their reactivity, then copper is less reactive than zinc. But at the same time, if we place one more metal, silver, then it is comparatively less reactive than copper. That means reactivity order will be silver is least reactive from these three, then we have copper, and then we have zinc. So it simply represents more reactive metals will try to convert themselves or they will try to produce ions, and less reactive metals will try to convert or try to produce atoms. So higher reactive metals will convert into ions and lower reactive metals will convert into atoms or metals. So that means when we place copper and zinc together, zinc will try to convert into Zn2 plus ion if it is in metallic state, and copper will try to convert into metallic copper if it is in ionic state, and these will be the final stages. If they are already in their final stages, then no further reaction will occur. That means if you dip copper rod into zinc sulfate or nitrate solution, no reaction will be observed. But if we keep these together, that means copper and silver, then silver being less reactive, it will try to convert itself into silver metal, and copper will try to convert itself into copper ion. And if they are already in their final stages, that means metal of silver and ions of copper, then no further reaction will be observed. And we can see it with the second example. In second example, as we can see, we have solution of silver, that means silver nitrate solution, and we placed a copper rod into it. Copper being more reactive than the silver, it will try to convert itself into ions. That means by losing electron, it will oxidize, and these released electrons will be gained by silver ions and it will convert into silver metal. And that's why, as we can see, initially we have colorless solution which will start turn blue in color, and copper rod will deposit some metals at the bottom, which is silver metal. So as the reaction proceeds, silver will convert in metallic silver and it will deposit on the copper rod, and that's why this whitish color will develop, and more copper ions will dissolve in the solution, and that's why you will see more and more blue colored solution. So this competition for release of electrons incidentally reminds us of the competition for release of protons among the acids. The similarity suggests that we might develop a table in which metals and their ions are listed on the basis of their tendency to release electrons, just as we do in case of acids to indicate the strength of acid. That means, as mentioned, zinc is most reactive from these three metals mentioned here, and silver is least reactive. So we can verify that with the given practicals. We can use the solution of one of the metal and solid metal of second metal. So when they connect, if reaction occurs, then we can represent that the solid metal is more reactive than the solution. And if no reaction occurs, then we can conclude that the solution of metal is more reactive than the solid metal used in the practical. But as a matter of fact, we already made the certain comparison By the comparison, we have come to know that zinc releases electron to copper and copper releases electrons to silver, and therefore the electron releasing tendency of the metals are in order of zinc is more reactive than copper and copper is more reactive than silver. So we should love to make our list more vast and design a metal activity series or electrochemical series. This series is already developed and you will learn about it in standard 12. We have a dedicated unit for electrochemistry. The competition for the electrons between the various metals help us to design a class of cells named as galvanic cell, in which the chemical reactions become the source of electron energy or electricity. We should study more about this in class 12. Now next is oxidation number. Now we already see some of the examples of oxidation number. Usually charges mentioned on the ions can be represented as oxidation number. A less obvious example of electron transfer is realized when hydrogen combines with oxygen to form water by the reaction. So here simple reaction is mentioned, H2 plus O2 produces H2O. Now in this case, if we compare this molecule with NaCl, then in NaCl we know that we have positive ion of sodium and negative ion of chlorine. But what about H2O? Because it is not ionic compound, so we do not have ions in water molecule. We can get ions in ionic compound, but in this case we have covalent compound. So though not simple in its approach, yet we can visualize the H atom as going from a neutral or zero state in H2, that means before reaction, to a positive state in H2O. And the atom O goes from zero state in oxygen molecule to di-negative, that means -2 state in H2O. It is assumed that there is an electron transfer from hydrogen to oxygen and consequently H2 oxidizes and O2 reduced. Actually, they do not release or gain electrons as we discussed in ionic compound, but we have to assume such thing. However, as we shall see later, the charge transfer is only partial and is perhaps better described as an electron shift rather than a complete loss of electron by hydrogen and gain by oxygen. So that means it is just the shift from hydrogen to oxygen. That means electrons of hydrogen will comparatively stay closer to oxygen, and we can assume it as just mentioned in case of NaCl, sodium loses electron to the chlorine. But in this case, hydrogen actually do not lose electron to the oxygen. So what has been said here is with respect to equation 8.18 may be true for good number of rather reaction involving covalent compounds, and two such examples of this class of these reactions are as follow. H2 plus Cl2 produces HCl and methane and chlorine. It produces carbon tetrachloride and HCl. In order to keep track of electron shift in chemical reaction involving the formation of covalent compounds, a more practical method of using oxidation number has been developed. In this method, it is always assumed that there is a complete transfer of electron from less electronegative atom to a more electronegative atom. So as mentioned, it is assumed. Actually, these type of reactions do not occur. That means in case of covalent compounds, electron transfer do not takes place. But we have to assume it. Less electronegative element will lose electron and it will enter into higher electronegative element. So from these given reactions, hydrogen and chlorine, when reacts together to produce HCl, we can assume it. Hydrogen being less electronegative, it loses electron, and chlorine being more electronegative, it gains electron. Similar situation when methane and chlorine combines to form CCl4, we can assume that carbon loses electron to the chlorine. So that's why we can rewrite the equations as mentioned here. Hydrogen and oxygen, initially they have zero oxidation states, and later when H2O produces, two hydrogen atoms losing 1 electron each gains +1 oxidation state, and oxygen gains 2 electron, and that's why its oxidation state will be -2. Similarly, in case of H2 and Cl2, hydrogen loses one electron, chlorine gets one electron. So oxidation state of hydrogen will be +1, for chlorine -1. For CH4, methane, it contains carbon and hydrogen. So we know that carbon is electronegative than hydrogen, and that's why carbon will gain electron from the hydrogen. We have 4 hydrogens, that means 4 hydrogen will donate 1 electron each to the carbon, and that's why carbon gets -4 oxidation state. Chlorine, it is atomic state, that means it contains similar type of atoms, so it gains 0 oxidation state. After the reaction, when carbon combines with chlorine, chlorine being more negative, it gains electron from the carbon. So carbon loses 4 electron to 4 different chlorines, that's why it gets +4 oxidation state, and each chlorine gets -1 oxidation state. And in case of HCl, just mentioned in previous reaction. So it may be emphasized that the assumption of the electron transfer is made for bookkeeping purpose only, and it will become obvious that in later stage in this unit that it leads to simple description of redox reaction. Oxidation number denotes the oxidation state of an element in a compound ascertained according to set of rules formulated on the basis of that electron pair in covalent bond belongs to entirely to more electronegative element. We know that in case of covalent compounds, electron pair present between two different atoms belongs to both of the atoms. That means when hydrogen and chlorine combines with each other, both contains 1 unpaired electron. Let's say electron of chlorine is X and electron of hydrogen is dot. So when they share this electron pair actually belongs to both of the element. But according to this oxidation rule, we will assume that this electron pair belongs to more electronegative element, chlorine only. And that's why we assume hydrogen as positive ion and chlorine as negative ion. Actually, they are not positive or negative ions at all. But to understand redox reaction, we will assume they are just like ionic compound NaCl. And from the next lecture, we will discuss about the rules how to calculate oxidation numbers.